The Metropolis algorithm is the original MCMC algorithm, and it was first introduced in 1953 in a paper by Metropolis, Rosenbluth, Teller, and Teller. And Metropolis gets sort of the credit. It's named after Metropolis, but it's not really clear how much he had to actually do with deriving or implementing the algorithm. But anyway, that's what we call it, the Metropolis algorithm. And the setup here is that we're given some PMF, let's call it pi, it will be convenient to call it pi, on a set of states x, we'll refer to them as states. And we're gonna consider the case when x is countable. So x is going to be a countable set. So this will be the discrete for a discrete distribution. Well, we call it a PMF, so it's clearly going to be discrete. And then we may also be given some function f on x, some real valued function. And our goal is we want to sample. So we have two possible goals. Either A, we want to sample from pi approximately for whatever reason, or B, we may want to approximate an expected value, the expected value of f of x, this function f, where here, where x is distributed according to pi. And the problem is that these, this pi may be super complicated. And this f may be complicated also. Sorry, that's a funny complicated. F may be complicated also. So computing this exactly is just intractable, and sampling exactly from this is not possible to do in an efficient way. So the approach that the Metropolis algorithm takes is to construct a Markov chain that has pi as its stationary distribution, and you construct the Markov chain in such a way that it's easy to sample from it, and then you just apply the ergodic theorem. The ergodic theorem tells you that if you run your Markov chain long enough, then you pick off the last state that you ended at, then that's going to be approximately distributed according to pi, and so that gives you a way to sample. And or the other part of the ergodic theorem tells you, as long as your Markov chain is ergodic, it tells you that, well, that's as long as it's ergodic, and as long as it's irreducible and has the stationary distribution pi, then you can approximate this expected value by using the sample mean over all the states that your Markov chain takes. So that's the approach, and I'm going to give you a sort of algorithmic definition of the Metropolis algorithm. So first we need to introduce a little terminology. A proposal matrix is just, we're just going to use that term to refer to a stochastic matrix. A stochastic matrix is just, it's non-negative, and all its entries, all its rows sum up to 1. So it's just some matrix Q, it's QAB as A and B. And so here it's going to be a matrix where the entries A, B range over this set of states X. And a notational remark is that sometimes, if I do this, then you know what I mean. Sometimes I write Q AB in parentheses instead of subscripts. So that's just a notational thing. Sometimes I switch back and forth between these two, so you don't get confused. Okay, so a note here before we get started with the algorithm is that oftentimes we won't know, or we won't be able to efficiently compute pi of x efficiently for any given value of x, but we can compute pi tilde of x, where pi tilde of x is proportional to pi. Well, pi tilde is proportional to pi. And z is some positive number here. So it turns out that the Metropolis algorithm doesn't require us to be able to efficiently compute pi of x. It just requires us to be able to compute pi tilde of x. And that's a very, very, very super nice feature, because computing, even though in principle, mathematically speaking, we could, once we know pi tilde, we know pi, computing this z can be very, very computationally difficult. All right, with that sort of introductory material out of the way, what is the Metropolis algorithm? So the algorithm is the following. First, you choose a proposal matrix Q, and you choose Q to be a symmetric matrix. So this is one thing which is special about the Metropolis algorithm, as opposed to, there's a generalization called the Metropolis-Hastings algorithm, in which this doesn't have to be symmetric, but for Metropolis, it does. So it's symmetric, and then the next step is you initialize to some initial state x0, and then we're going to do the following iteration. For I equals 0, 1, 2, up to n minus 1, we'll take the following steps. First, sample, let's call it x. We will take draw a state x from the distribution. So here I'm using this, putting it in parentheses here. From the distribution qxi x, where I mean you fix xi, xi is already known at this step. It's either x0 when I is 0, or it's the previous thing that we sort of know. And when I say this, I mean all the numbers q, xi, comma x, as x ranges over all the values, all the possible states. So you sample x according to that probability distribution. So in other words, I could write it this way. Probability of x given xi is this number here. So we sample x, that's our proposal. That's called the proposal. Then we sample a number u from a uniform distribution on the interval from 0 to 1, just a simple standard uniform random variable. And then, so we're going to either accept or reject this proposal according to a random criterion. And the randomness comes from u, and the criterion is the following. If u is strictly less than, well, it doesn't matter that it's strictly. If it's less than pi tilde of x divided by pi tilde of xi, so it's the well, it's not the probability, it's it's proportional to the probability of x. That's where we're using pi tilde. And the reason, by the way, the reason why we can use pi tilde, it turns out, is in this step is because the z's cancel here. Just a parenthetical remark. So if u is less than this, then we accept. So we take xi plus 1 to be x, and otherwise we reject, and we take xi plus 1 to just be xi. So if you imagine sort of a sequence, we're getting a sequence of states, and if we reject, we just keep the previous state. That's xi plus 1 equals xi. And if we accept the proposal, then we take the new state, the proposal. Okay, that's it. I mean, that's the algorithm. And then you output, so you run that n times, and your output is a sample from this. Well, this generates this sequence of numbers, or a sequence of states at least, and that's the output of the algorithm. So the first step here was in each iteration was the proposal, and the second step here was, accept or reject according to that random criterion.